All right, let's go over the grading guidance here. It's not great, and I chose this one specifically because it's not great, but it's an appropriate question and has appropriate stuff in it. But more importantly, I chose it because it's very achievable if you don't quit. If you quit, you can't do this problem. It's got stuff in it that just stinks and is hard. But when you see the point totals and you understand that if you don't quit, you're very likely to do incredibly well on this test. So let's take a look at it, and we'll talk about the point totals that were given on this test at the very end. But we'll do the grading as if we're normally doing grading. So break out your red pen and your highlighter, and let's go through it. So starting with part A. In this problem, they want to talk about a spring that's a weird spring, and it has this. This is the force on the spring. So believe it or not, to get the credit for part A, you only get 2 points. 2 points for the derive the expression. And I think this is reasonable. It comes down to the work done equals the amount of energy stored, and that's going to be f dot dx. In this case, the f dot dx is going to be as squared plus bs ds, where s represents how far the spring is compressed, and we're going to do this from 0 to s. It's a little weird thing, but remember, the idea is that you're compressing this spring, and therefore the energy stored in the spring is based on starting at equilibrium 0 and compressing at a distance s. It's a polynomial. So the first one is going to be take s, add 1 to the 2, and get s cubed, and then divide by the new exponent. And do that for the next one. I have s to the 1, add 1 to the exponent, so that's going to be s squared, and then divide by the new exponent. There it is, and then evaluate this from 0 to s, which gives us, let's see, the amount of energy stored is going to be a over 3 s cubed plus b over 2 s squared. A little messy there, but you get the point. 2 points. And there's 1 point is given for any indication that you understood that you had to do this. That's 1 point. And then 1 point was given for understanding that you're starting from 0 and going to s, and that you have to integrate. Nothing was talked about when it comes to the sign. And the truth is, there's issues with the sign. The force should have been in the opposite direction of the displacement. There should have been a whole cosine of 180 in there. They just want to know how much energy is stored. As long as you know the energy is going into the spring, you were fine. Trust me, there's stuff later where, direction's going to be an issue, but this one's not so terrible. So let's start there and let's go on from there. So next is the next page. You couldn't do this portion. It's hard to do the next portion. So you have to have something that you can use to make the next portion work out. Here we go. So the first two questions talk about the speed of the cart immediately after it loses contact with the spring and the impulse given to the cart. Now, here's the thing. You're going to get full credit as long as you have some understanding of what the energy stored in the spring is. Now, I'm going to use, of course, the correct answer, but please understand that if you don't have that correct answer, what were you going to use? You need something. And part B number 1 is worth 3 points, and part B number 2 is worth, 3 points as well. So the real question comes down to, do you have something that you can use here? As long as you got something for part A, you got full credit. Now, if you got nothing for part A, what are you going to do here? Use a regular spring. Use 1/2 kx squared and pick A or B to be k. It doesn't matter. They don't give any credit for using the right answer from part A. They give credit for using whatever you got in part A. So have something. It's a spring. Either way, to do this correctly, here's what I did. I started with the amount of potential energy going to be equal to kinetic energy. That was worth 1 point. And then for using the expression for potential energy from part A, okay, And a correct expression for kinetic energy. That one's easy. So I used my 200 over 3 times 0.04 cubed plus 150 over 2 times 0.04 squared equals 1/2 mv squared. That's what I used. And they gave 1 point for this, 1 point for any expression that you got in part A, and 1 point for knowing what kinetic energy is. That's all 1 point. And then 1 point for solving for V. So V equals 0.91 meters per second. That's 1 point. So even if you just used 1/2 kx squared, you get this 1 point. Not terrible. Now, B number 2, you had to know something for B number 2. You had to know that impulse was either force times time or change in momentum. One of those helps you and one of those doesn't. This one doesn't. You don't have force as a function of time. You do know the change in momentum. It started from 0 and ended at mv. And here's the amazing thing. If you just made a statement about impulse, you got a point. If you made a substitution into delta P, you got a point, which is going to be mv final minus mv initial, which we would be doing v naught and v, but let's just leave it like that. That's our change in momentum. And then it's just using whatever you got for the velocity before and saying 0.3 times 0.91 minus 0.3 times 0. And getting your expression to be 0.27 and units, kilograms, meters per second, got you the impulse. So 1 point for a correct expression, 1 point for subbing in, and 1 point for getting an answer. 6 points here. 6 points for just that. Right now, between B number 2 and B number 1, that is 6 total points. Plus, there's the 2 points you get for part A. We're at 8 points. 8 points for the first FRQ. If you got those, you're already at the border. You've got a 3, you're working on a 4. Now, in a good argument is to go on to the next part where you had to deal with this. And none of the stuff you've done so far has anything to do with this. You had to graph it, and they did not make this easy for a number of reasons. One, when you look at the starting and finish velocities, you know, they go from 0.4 to 0.3, but they give you, you know, this. So if you want to start from 0, it's going to be hard. And the bottom part is pretty easy. They give you decent places to hang this one. So I think that's, you know, that one's fine. You know, make sure you put in meters, and put that you're talking about the m, the position. Velocity, that's going to be harder. I decided to scale it, and I tell everybody you're always supposed to start from 0, and this should start from 0 too. But it's hard to use something that's divided by 4 and go a little bit more than 4, and you have to go a little bit more than 4 twice. So you're not going to like this because I've told you always to do something different, but it was just too hard to do that. So I decided to go, what do I do in my notes here? 2.25, 3.25, and 4.25. Because I knew that would make this 2.75, and this would be 3.75, and it would be pretty easy for me to set this up. And then I just took my things, 4.12, so that's like here. And 4.07, let's see, that's 0.85, 0.95, 4.07, it's gonna be like right here. And then 0.6 is 3.99, that's at 4, so that's 8.8595, so maybe I shoot this up, but it's gonna be about there. And then 3.74, that one's easy because I have 3.75, and then 3.38, that's pretty easy, 2535, so that's gonna be like right there. So probably this point I graphed wrong, so maybe, or this point I graphed wrong. So let me see, this is 8595, 405, 415. So no, I probably should move this one up a little bit. But you know, they're not giving that much for this. You only have a limited amount of time, so I didn't want to waste too much of it. So this is what I did, and the way they gave points is not crazy. They said, okay, so 1 point for correctly labeling the axis with your unit. So I didn't put, I need that velocity. Come on, velocity and meters per second. And position and meters. All right, so label my units. For correctly scaling both axes, that one, you may or may not get that point. And for correctly plotting your data points, definitely plot your data points. It's clearly nonlinear. So let's move on to what the questions are. D number 1, compare the speed of the cart measured by photogate 1 to the predicted value of the speed of the cart. They expected the cart to be traveling at, where is it? 0.32 meters per second, and at the first gate it's 0.412 meters per second. What are you going to put there? I put that he pulled it back too far. And let's see, pulled back cart farther than indicated. You could say too far, but indicated makes it sound like it's smarter. D number 1 is only worth 1 point. So you do need to say that, and I said it but didn't write it down, that the cart seems to be going faster than it should be. The predicted value was 0.32. The actual value at photogate 1 was 0.412. You need to indicate what's wrong and then indicate what you think the problem is. There's lots of things you could say. The table wasn't level, so it sped up. You could say that he pulled back too far. There's just several different things you could have said. Or maybe they didn't measure the constants A and B correctly. All of those work. The threshold for getting those points is pretty low, but it's only 2 points total. And then it goes on, from the measured speed values of the cart as it rolls down the track, give a physical explanation for any trend you observe. Obviously, the cart is losing velocity, and it shouldn't be. So what's happening? I said the cart appears to be slowing down. You need to observe the trend. So I observed the trend. The cart is slowing down. And then the next thing I said is probably air resistance. This was 2 points. What's the trend and what's your explanation? So they said friction in the axles, air resistance against the cart. They were pretty flexible in allowing you to have those points. So this is one of the, again, I'll say it again, if you can persevere, nothing on this page had anything to do with what you did before. You could have started this page fresh and not really have done anything before that, and still it was worth 3 plus 2 plus 2, 3, 4, 5, 6, 7 points. All right, moving to here. This one is a tough question, but the really hard math stuff doesn't start till the last part. A lot of this, not terrible. For example, the box slides down the ramp. How fast is it going when it makes it to the bottom? Did you say conservation of energy? Because if you did, and you worked it out, saying maybe gravitational potential energy equals kinetic, mgh equals 1/2 mv naught squared, and therefore v naught squared equals the square root of, wait, we're not solving for v. What am I doing? We're solving for h. So even easier, h equals v naught, h equals v naught squared over 2g. That is it. They gave 1 point for any expression of conservation of energy, 1 point for correct substitution in the expressions for potential energy and kinetic energy, and 1 point for solving for h. 3 points. And they let you use motion equations if you really wanted to, although that would have made it harder. So question B, I think a lot of students don't get the points for question B. They don't check 0. But it says, a short time after passing point P, so we're on the table, the block is in contact with the wall. and moves with the speed of v. Is the vertical, that's the big word here, vertical component of the net force on the block, upward, downward, 0. It's 0. The block is not accelerating upwards. The block is not accelerating downwards. It's on the table. So the net force is 0. It's not accelerating up or down. That's it. 2 points. All you need to say. So it's 2 points. You get 1 point for correctly indicating 0 and 1 point for correct explanation as to why. And it's not accelerating up or down. That's a good thing for why. B number 2, I think students probably get this wrong. It's worth 3 points. 3 points. And all we're talking about is drawing an arrow and justifying. So did you draw your arrow like this? I don't know how many of you did, but there has to be 2 contributions to the force. So for drawing a single arrow pointed in the third quadrant, 2 points. For correct justification for both components, 1 point. Well, one component is there has to be an unbalanced force this way to make it travel through the circle. It's in contact with the wall. There must be a normal force from the wall, period. It's that simple. If it's touching something, it applies a force. We've talked about that. And the wall has a coefficient of friction of mu, so there must be friction in this direction. You get 2 points for 1 point for this arrow and 1 total point for your justification. Now, you don't have to draw it like this. You're not supposed to draw components. You're supposed to explain the components. So you draw this and you say, well, there's a force to the left due to the normal force from the wall and a force downwards due to friction. That's it. That gives you all 2 points for this one. Not terrible. Oh, wait, I'm sorry. 3 points for that one. 3 points. It is 2 points for the arrow and 1 point for your justification. So 3 points for that one. So, wow, lots. So part A was worth 3 points. Part B is worth 2 points. And we are now at, a total of 8 points. 8 points. So you're passing the exam now. Did you stay with it? Because now we got part C. Here we go. Determine an expression for the magnitude of the normal force exerted on the block by the circular wall as a function of V. C is worth a whole 1 point, and deservedly so. Although a lot of you will freak out because of that. Net force equals MAC. So this part is mv squared over r. This part, normal force. Done. 1 point for that. Let's go to part D, which is worth 3 points, and deservedly so maybe. Derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained speed v. So we get to use v in our answer, and we know the normal force. So first, they want you to be able to state that the frictional force is slowing down the object. So can you say that basically this is a statement of Newton's second law? Now, they're indicating that it's about magnitude. So if you don't have the negative sign, that's fine, but that hurts you on question E. So if you just said friction equals MA, you got full credit. And if you then said that mu times the normal force equals MA, you got another point for indicating that friction equals mu times the normal force. So this last part is subbing in for the normal force and solving for the acceleration. We have an expression for the normal force from part C. So mu, and if we're going to put in the mv squared over r equals ma. And then all you have to do is cancel out the m's and you have your answer. So part D, worth a solid 3 points. And yeah, not terrible. Not terrible. If you don't have the negative sign here in your answer, you get full credit because it asks for the magnitude. But then there's question E. Now, arguably, question E is tough. Question E is worth a total of 3 points. How long are you going to spend on it before you realize you can or can't do it? It's a tough one. I'm not minimizing that. But you've got 45 minutes total, and there's still a whole other FRQ. So how much time are you going to spend doing question E? And we've talked about it. Question is tough. So let's talk about derive an expression for velocity as a function of time. We just solved for acceleration as a function of time. And we got, and we got, minus mu v squared over r. So to derive an expression for velocity as a function of time, we have to use a differential equation. I know, calculus on 2 questions on the same exam. And luckily, this is the last part. Can you do it or not? You get 1 point, 1 total point for just doing this. If you made that assessment from the prior part. Now, I know you're in the middle of the test, you're freaking out, it's hard, you probably won't think that way. But derive an expression, when they say derive an expression for velocity as a function of time, it's really pointing towards a differential equation. Now, you got a point for including this negative sign. So 1 point for doing, sorry, I wrote that wrong place. 1 point for any substitution for dv over dt for a, and then 1 point for putting in the negative sign. Everything else is 1 point for getting an expression. Everything else. So if you get this far, 14 out of 15 points. The rest of it, which I'm going to do, is worth only 1 total point. I'm going to separate the differential. I'm going to collect the variables on the correct side. I'm going to integrate both sides and set the appropriate variables. 0 to t starts at v naught and goes to v. It makes it to the bottom at v naught. That's why I have to do that. Taking the antiderivative of the left side and getting negative 1. Oh, well, let me do it this way. This is 1 over v squared, which is actually v to the negative 2 squared. So adding 1 to my exponent and dividing by the new exponent and setting my limits from v naught to v. That's the left side. The right side, there's no t there. So pulling out my constant and assuming a t to the 0 power, my antiderivative will be t to the 1 power. And then evaluate that from 0 to t. All right, so this is going to be negative 1 over v minus negative 1 over v naught equals negative mu over r times t. Again, this is all worth 1 point. So keep that in mind. I have to solve for v now. So I'm going to move it to the other side and move this to this side because these two are positive. So I get 1 over v naught plus mu t over r equals 1 over v. I get common denominators in a situation like this because I'm going to invert my answer. So v naught over r equals r plus mu t v naught. That equals 1 over v. So v equals v naught r over r plus mu t v naught. All of that 1 point. All right. It's a big one. It's a big one. So there we go. I'm not even sure what to do here, so I'm going to leave it like that and then go on to booyah, this one. This one's not terrible, but I think a lot of students did badly on it when they actually took it that year. So he throws the ball and it's a projectile. It does one of those. So let's just talk about it. Derive an expression for the length of time it'll take to strike the ice. It says derive. So whenever there's a derive, remember you've got to show where you get your points from, but A is only worth 2 points. So I'm going to use delta y equals 1/2 a t squared plus v y naught times t, which is going to be negative h equals 1/2 times negative g t squared plus 0. So t equals a square root of 2h over g. 2 points. 1 point for the equation, 1 point for solving it. There's not a lot there. Question B. Assuming that the disc is free to slide on the ice, derive an expression for the speed of the disc and person immediately after it's thrown. Conservation of momentum. He throws it horizontally. So conservation of momentum. The momentum before he throws it is 0. The momentum after he throws it is going to be mass of the person plus disc times v plus mass of the stone times v. That's it. So they want me to use v naught for the velocity of the stone. So let's see. This is the person has a mass of m over 2, and the disc has a mass of m, v, and the stone has a mass of m over 20 times v naught. So there's a v and there's an m in every term, so I can get rid of all of those, and this is going to be 1/2 plus 1, or 3/2 v plus 1 over 20 v naught. Common denominator, I think. So actually, I'm not common denominator. I'm solving for v. What am I talking about? So that's going to be negative 3/2 v equals 1/20 v naught. So I'm solving for v. So multiply both sides by 2/3, and I get that v equals minus 1/30 v naught. They gave 3 points for this, and it was 1 point for any statement of conservation of momentum, 1 point for substituting the momentum of the stone into the correct expression, and 1 point for substituting the momentum of the person disc system. There was no points actually given for solving. And they didn't care about the negative sign since it asked for speed. So 3 points for part B. Moving on to part C, derive an expression for the time it will take the disc to stop sliding. All right, that's a toughie one. The disc and person is sliding this way across the non-perfectly smooth surface. So here's my surface. Basically, normal force, weight, which is 3/2 mg, and friction. So we're interested in the time it takes. You could say net force equals ma, and then use that in a motion equation. Or you could say impulse equals change in momentum. They both work out exactly the same. They're both pretty straightforward. I think most students probably do this. So let's do that for this example. Let's find the acceleration. So, not terrible. Net force equals ma, which is actually 3/2 ma. The net force is minus mu times the normal force, and that equals 3/2 ma. And the normal force is 3/2 mg, which equals 3/2 ma. So cancel out the 3/2 and all that, and I get that the acceleration equals minus mu g. Fantastic. So now v equals at plus v naught. V naught is going to be actually the 1/30th the initial velocity. So this is going to be 0 equals minus mu g t plus 1/30th v naught. So solving for t, I get t equals v naught over 30 mu g. Oof. Now, that's part C. It's worth 3 points. There's 1 point for indicating that you can figure out what the size of the frictional force is. 1 point for substituting the velocity from part B in correctly, and then 1 point for actually solving for the time. It's kind of funny how you get points here, but that's the way they go. Whew. All right, now we're on to the end. This bad boy here. Last page. Boy, we're tired. We've done two FRQs. We're halfway through the last one, and you only have so much time. So the person now stands on the ice on a similar disc M, radius R. It has a fixed pole through its center. So that's not let the system move. It is a pivot point. So it can rotate on the ice. So it's now on ice. The person throws the same stone horizontally in a tangential direction at initial speed v0, as shown in the figure above. The rotational inertia of the disc is mr squared over 2. Derive an expression for the angular speed of the disc immediately after the stone is thrown. All right. What was the momentum before? The momentum, and I'm doing angular momentum, is 0. What is the momentum after? Well, what things have momentum? There are two things. The stone has momentum, and the disc has momentum. What's the stone's momentum? Oh, I'm going to use R perpendicular mv. And what's the disc's angular momentum? I'm going to use I omega. So that's going to be R. Mass of the stone is 1 over 20 m, and the velocity is v0. This part though, let's work that over here. I is, be careful, I is the disc plus the person. So 1/2 mv squared plus m over 2. Why did I say v squared? Because I'm getting tired. 1/2 m r squared plus m over 2 r squared. That all comes out to mr squared. So plus mr squared omega. That still has to all equal 0. So now our job is just to find omega. I'll point out m cancels. One of the r's cancels. And so working that over here, omega is going to equal, looks like v0 over 20r. Now what's amazing, 4 points here, 4 points. So to get all 4 points, any statement of conservation of momentum, 1 point. Any statement that you understand that the rock has a angular momentum equal to rmv. Any statement that the disk and person system has a angular momentum equal to I omega. Am I right for that? Oh, I'm wrong. Let me back that up a little bit. Yikes. So it is 1 point for all of that. 1 point for a statement of conservation of total angular momentum, and then 1 point for substituting the angular momentum of the stone into a correct expression for the conservation of angular momentum. So 1 point for starting with this and getting that. And then 1 point for substituting the angular momentum of the person into a correct expression for the conservation of angular momentum, and 1 point for substituting the angular momentum of the disk into a correct expression for the angular momentum. We did them here, so 1 point for combining the moments of inertia, and 1 point for substituting them into a correct expression for the angular momentum. So 1 point there. And then one final point for actually solving for the expression for velocity. So 1, 2, 3, 4. 4 points. Oof, that was a mess. Good. Let's go to the last part. Believe it or not, question E is 3 points. And it says the person now stands on the disc at rest, r over 2 from the center of the disc. The person now throws the stone horizontally with a speed v0 in the same direction as in part D. Is the angular speed of the disc immediately after throwing the stone from this new position greater, less, or equal to the angular speed found in part D? And justify your answer. Hopefully everybody put less than. It's worth a point. And then 1 point for correctly identifying a decrease in the stone's angular momentum. R perpendicular MV is less. And then 1 point for correctly identifying that the person also adds less inertia, but with less angular momentum, the whole system will have less velocity. So the justification is a little bit ambiguous, but it's 1 point for indicating during your justification that him standing towards the middle reduces the angular momentum of the moment of inertia of the system, but it also has less overall momentum. So with less overall momentum, there's going to be less velocity. But by quickly, this whole video is like 35 minutes. So if you're watching still and you're still grading, yay, good job. Way to go, you're the best. All right, see y'all tomorrow.